Now you got a preview of my presentation. Um, Thank you all for staying on. I know sometimes it gets a little long by the time you get to this point. I also have to apologize. There's a little background noise in the facility I'm in right now. I'm at the same place that Matt was when he presented. Um, okay, so I'm going to talk about irrigation filtration, and there are things I'm going to talk about that may apply in the context of some of the water quality things we've been talking about. But in general, I'm focusing on conventional filtration. So I'm not going to talk about things like reverse osmosis or other things that are typically not feasible with the quantities of water we're normally irrigating with. So why filter? That's kind of an obvious question, but here we are on a remote meeting, and so we have to have lots of slides. So I'm going to focus on drip irrigation and sprinklers, because if you're not irrigating with sprinklers or drip irrigation, you probably aren't filtering. But I wanted to give an idea. Okay, so we've got lots of different types of drip emitters. If you've got drip tape of some kind or drip tubing with embedded emitters, they're going to look something like this clear one here. Hopefully you can see my mouse. And the water in these devices enters a channel. It goes through a path that zigzags back and forth and into a chamber and then out. There's usually a little hole or a slit cut in the wall of the pipe here, right? So whatever water travels in there has to be clean enough to not clog the emitter. Another type of device is here. You can see a small opening that's like a little screen, hopefully on this one that's a purple cutaway. If we use button emitters, then it's got to be small enough to enter that barbed and pass through the diaphragm or other feature of the interior of the emitter. Okay. For sprinklers, it's a little more simple. We have a nozzle in a lot of our rotating sprinklers. Sometimes the actual nozzle is hidden, as it is in this device. And this is just a distribution tube here that rotates around. So you've got basically two orifices that you've got to watch out for. Here is a lawn sprinkler, usually just a single orifice. So what are we filtering out? Obviously, large things, leaves and debris that would clog sprinklers, sometimes large enough to cause problems to pumps, valves. A big one, algae and other organics. So I have this photo of filamentous algae. If anybody has that in their irrigation water source, you know it, because it's a real pain to work with, and it's a real pain on the filtration side. I put fish. I realize that in the context of this workshop with small and urban farms, this is not usually something we're concerned about. I spent a few years as a consultant for an irrigation engineering firm in the lower Columbia Basin, so Oregon, Washington, and we would deal with the Army Corps of Engineers regulations. When you had a direct diversion from the Columbia River, you had to have a filter that would not allow salmon fry to get sucked into the pumps. And so you'd have a fairly fine screen, and then it had to be very massive so that the velocity of water entering that screen was so slow that the fry wouldn't get trapped against the screen. So one kind of extreme end of filtration, but I just thought was kind of fun to mention. A lot of times we also have inorganic materials. We may be trying to exclude sand from the system, which could settle and cause clogging issues or also abrasion issues. Sometimes silt, but you'll notice how small silt is. We're going to usually have a difficult time filtering silts. Clays, we're not with conventional filtration, we're not removing clay particles from the water. Now, clays, we call them colloidal because they are colloidal. And so they are solids that stay suspended in the water. Usually clays don't cause huge problems, but we'll talk about some cases where they can. All right. So if you haven't worked with filtration a lot before, it's helpful to be familiar with the concept of mesh size. Most filters are sold based on a mesh size, with a larger size being a smaller particle that would be trapped by the filter. So usually in irrigation, we're talking about something in the when I say usually, I mean for like drip irrigation, small sprinklers, we're going to want to filter at the 80 to 120 mesh size. Some drip needs even down as low as 200, and some sprinklers can get by with quite coarse screen. If you're smaller, if you're trying to get particles larger, see this is about 1/8 of an inch up here at a 5 mesh. If you're talking about larger particles than that, then you're just talking about porous screen, and the dimensions are a little different. You'll get a copy of these slides for your reference, but you can also just search mesh size and get an idea really easily. When we look at mesh size for different irrigation devices, it really depends on the device itself. For larger devices like a conventional sprinkler, so we're talking usually a sprinkler as opposed to a micro sprinkler is going to be a device where we measure flow in gallons per hour. If you're your irrigation dealer or hardware store, there will be a flow range or something on that device, and it will be in sorry, I said gallons per hour, but it'll be in gallons per minute, often 1 gallon per minute or larger. For that, we typically call that just a sprinkler as opposed to a micro sprinkler. And what we want to do with a sprinkler is we need to filter out any particles large enough that two or more particles could come together and bridge the nozzle to clog it. Okay. Usually we can get by on that half the nozzle diameter. Most sprinklers will have some indication of the diameter. If it's a landscape sprinkler, they don't have round diameters. And so you might have to look. Sometimes the sprinkler will say the filtration requirement, or you might have to kind of estimate the size of that outlet based on the device when you look at the nozzle itself. But often, our outlets for these types of sprinklers are going to be a 1/16 of an inch or larger in diameter, which means that we need to filter out anything 1/32 of an inch or larger. Okay. So that gives you a general range for most sprinklers. For a micro sprinkler, I use the same little sketch I made, but for micro sprinklers, we start to get into a range where really small particles, we're no longer filtering out or worried about sand particles. We're talking about particles that are in the silt range being able to clog these sprinklers. And those particles can often bridge with more particles. So a rule of thumb used by Charlie Burt and others at California Polytechnic University in San Luis Obispo, is 1/7 of a sprinkler nozzle diameter. These are for really small, for micro sprinklers. Often the minimum mesh size will be provided by the manufacturer. But just know that this is a general rule, 1/7. So you're talking about 6 to 7 particles being able to bridge together and clog this nozzle. So we often have sprinkler outlets in the 32nd of an inch range to maybe 1/10 of an inch range. So you're talking about filters that are in this 4 thousandths to 14 thousandths of an inch range. Okay. With drip, it gets even worse. We usually need to, the rule of thumb is that we filter out particles 1/10 of the outlet diameter or smaller. Part of that may be that sometimes the pathway inside the emitter is actually smaller than the emitter outlet diameter. And also that we're getting into a small range where particles adhere to each other better. So we're often looking at outlets in the 1 to 7 hundredths of an inch range. And so we're filtering to the 1 to 7 thousandths of an inch range. Pretty small. If we go back to this table, we can see that 7 thousandths of an inch is about 80 mesh where I mentioned. 1 is down at 600. Very rare that we get that small. It's common for drip to require something in the 120, maybe as small as 200 mesh range. Okay. So we have a couple different kinds of filter. If you are pulling from a surface water source, a canal, a river, or just a secondary water supply, but it's not pressurized. For example, at my own house, I have secondary water, but it's very low pressure, so I have to pump. So often we'll need some kind of screen upstream of the pump to avoid damage to the pump itself. Usually we want that to be a pretty coarse screen. We don't want it to be easily clogged. What I've got a sketch here of is just a cylinder screen that would go in a river or canal and then hook up to a pump suction, for example. A lot of times these will look like a can that's kind of Swiss cheesed or has some expanded metal screen or something, usually a fairly coarse screen. Then we have fine filter screens, which I'd call maybe final or primary screening, where we can have quite a range. Notice this goes typically from 50 to 200 mesh. That's a huge range. 200 mesh is plenty for a lot of drip applications. 50 would be plenty for a lot of sprinkler applications. Screen filters, usually we have a flow coming in, pressurizing the inside of a screen, of a cylindrical screen, and then water moves out into an annular space and then out an outlet. Here's a picture I took last night of a little tiny screen I have on a hose bib at my house. It's these you'll see often at irrigation supply stores. When I take off the cover, here's the screen. So you have the cylinder, but it's the interior that's the actual filter. The exterior here is clean water. So when you clean it, you have to clean the inside. A downside to screen filters is they don't have a very large screen area, so they clog easily. And if the scales used at a lot of urban small farm scales, often they are manually cleaned. Another type of filter that's very common for this scale of irrigation system are disc filters. I actually really like disc filters. I don't sell them. So if you feel like I'm giving them too much hype, I apologize for that. But I really do like disc filters. Um, Disc filters kind of similar when we look at it. There's a spring inside that compiles a stack of discs. Water flows from the outside of the filter in to the discs and out the middle. So it's the opposite of most screen filters. Here is an image of one. Looks a lot like a screen filter. In fact, many brands make a similar filter body, whoops, for both screen filters and disc filters. So you cannot tell often without opening them what kind they are. Notice that when I unscrew the case, the springs decompress, and I should have taken a close up. The discs have diagonal slots around all the way around both faces that line up actually crosswise with diagonal slots on the disc on either side of it. So when they're pushed all together by that spring, there is actually quite a large filter area inside the discs. And then when you clean them and you remove the compression from that spring, you can rinse off between the discs. So what I like about a disc filter is the increased filter area and the ease of cleaning. However, most that are practical on a small scale still require manual cleaning. Sand separators are another option. If you happen to have a very sandy water source, you will find that that screens and disc filters they may not cut it. So there are devices called cyclone or vortex sand separators. I don't have a good picture of one, so I apologize for that, but here's a sketch I made. The idea is that you have water come in and it comes in on a tangent of a round vessel. Okay. So this is really all that it is. It's just a big vessel with the water comes in and it hits that wall and swirls around. Well, that swirling accelerates sand particles out. So the larger particles kind of get flung out against the wall of the filter or of the separator. They fall downward because of gravity and kind of accumulate at the bottom where they can be flushed out. Clean water kind of works its way up through the center of the device. A sand separator is a primary or kind of a first stage filter. You would need another finer filter usually after. But again, this is only going to work for large particles like sand, not as effective for things like leaves, algae, other organics. Okay, so now we talked about types of filters. There are others that are typically used in larger systems like sand media filters, or what we just call media filters now because they often have a filter media that's not sand. And we have self-cleaning filters we'll talk a little bit about. Okay, when you're sizing a filter, you select a filter based on the mesh size. Okay, how fine of a screen do I need, or a filter area like the discs? What do I need to be able to filter out? But you also need to make sure that you have plenty of filter size for the flow you're dealing with. A lot of manufacturers of filters will sell multiple sizes or make multiple sizes for a given filter model. And they will usually have a graph that looks like this. Okay, I just made this one general, but the idea is that you'll have different sizes of filter, small, medium, large. And for a given flow rate, there will be a certain amount of pressure loss across that filter. In fact, filters often have a pretty good amount of filter loss. So you have to decide how much pressure can you afford to lose across the filter. Do you have 2 pounds per square inch available? Do you have 5? 5 would be on the high end. Usually we want to keep it so that they're losing a couple pounds or less. And so you would decide that and you would come over, you'd look at your flow and you would select a filter that at your flow rate would be well below your required pressure loss. Because these graphs are usually for a clean filter. It's going to be worse as soon as you start accumulating things on it. If you have dirty water, you may need to oversize your filter or use multiple filters. Okay. And it may change year to year. I'll tell a little story here. I'll go back to this picture. In the bottom of this picture in my yard is the primary filter for my sprinkler system. This is a disc filter. It's an 1.5-inch line, I believe. It might be 1.25-inch line. I think that's what I have running everything. Anyway, but I've got an Amiad disc filter, okay? Most of the time it works great. I don't have to clean it very often. It's more than enough. In 2023, when there was a big spring runoff, we got a whole lot of filamentous algae. And I had to clean that thing at a minimum every irrigation, and sometimes more than that, because that algae would clog it off. So if you're running into a situation like that, you're better to have a little more filter than to have the system get choked off. Okay, this is an example of what would happen. Say we picked one of those filters. In this example, I picked that medium filter, and if we start getting clogged, what happens is that blue pressure loss curve starts to move upward. And it moves upward kind of proportionally. So more flow, more loss. Okay. All right. Now, here's the problem for the system. This product, this is a Netafim Typhoon. This is a commercially available drip line product, drip tape. This is for about a 0.5 gallon per hour product. So a lot, if you're buying drip products that are meant for agriculture, this is on the big side for discharge, about 0.5 gallon per hour. If you're buying for landscape, this would be on the small size. Landscape usually uses about 1 gallon per hour per emitter, and sometimes agriculture is as low as 1/10 of a gallon per hour per emitter, but you get the idea here. The emitter discharge for most drip products is related to the pressure. They're usually rated at what they do at about 10 psi, as is the case here. Now, what if my filter's clogged and is losing 2 more psi across the filter than normal? Well, in this case, that is somewhere in the 10 to 15% of flow reduction. And it gets worse and worse the more you get clogged. So that then you're not applying the water that you thought you were for the same application set time. I want to take just a second and go back to cleaning methods. I had mentioned about manually cleaning filters. Well, That's what I'm calling here the brute force method. You turn off water, you open the filter, and you clean it manually. Really effective. It can be quite time consuming, especially if you have a fairly large system or you can't be present all the time. There's another kind called a hand crank, and I'm actually not a very big fan of these. These will be for screen filters. And what you do is there's a brush that goes on and kind of spins around the inside of the filter. And you open a little valve at the bottom of the filter while you run the little brush, you open the valve and it shoots stuff out of there. Um, they can work, but it's not going to be as good as the brute force method. And it's not it can be done while you're running, but they tend to not be quite as good as you wish. There are also automated systems. They almost always require multiple filter bodies so that you can run clean water through one, so you can run clean water back through the other to clean it. Those are available for disc filters, for screen filters, usually cost substantially more than manual filters. Very uncommon to find automated filters less than several $1,000s. Okay. Where are we going to put the filter in our system? If you have a pump, you'll have a screen, I already mentioned, often upstream of the pump. We usually want the filters after the pump. There's a couple reasons for this. One is if the filter gets clogged, it is better to have the pump pushing pressure at the filter than sucking against the filter. It's much better on the pump. I took a photo, but I didn't add it to the presentation. But I have a pump that I'll admit to owning. I have for I guess various reasons. I have the filter upstream of the pump. It's just how it works on that system. It's actually the filter I already showed you a picture of. But if I'm not real careful in making sure that that filter is clean enough, it can choke off that pump, which it has done. And then the pump has gotten warm enough that it's blown PVC fittings off of the outlet. Super cool. Really like that. Makes me feel really intelligent. So if you have chemical injection, fertilizer, fertigation, okay, which is the next presentation, often we filter after we do that, or we'll have some pre-filter and our final filtration will be after chemical injection. Okay, what else? In my 1 minute, there are particles you can't filter out. And so it's important to remember line flushing. This is a commercial onion farm, but even small systems, especially drip, we should be flushing sediment out of the lines regularly and not relying on filtration for that. Okay.